There it started. And you can kind of click it in place however you want to do it.
Okay. So these are the Galilean moons. And they're one of his great discoveries. This is the discovery of that Galileo made of Venus. Now, Venus sits closer to the sun than the Earth does. So here's Venus going around the sun, and here's the Earth going around the sun. And you can see Venus would have phases. When Venus is kind of in line with the Earth to the sun, that would be a new Venus, kind of like a new moon. You can't really see Venus at all in that place. But when Venus swings around this way, and Venus actually goes faster around the sun than the Earth does, it's pretty regular law. The further you are away from the sun, the longer it takes you to go around, and the slower you move. It's a thing that having to do with gravity, which we'll talk about tomorrow, Isaac Newton. Anyway, you can see if Venus were right here and the Earth was here, you would see a half Venus. If Venus is on the other side and the Earth is here, you see a full Venus, kind of like a full moon. And if Venus is over here and the Earth is here, you would see a half Venus. So Venus has phases. Who cares? This is more proof that the sun is at the center. Because if we use the Earth-centered idea of what's the guy's name? Of Ptolemy. Let's look back at the Earth-centered. Whoops, I went past it. Let's look back at the Earth-centered idea. If the Earth was at the middle, and Venus was going around the Earth, and the sun was outside of that, you wouldn't have the same phases that you do with a heliocentric model. If Venus did epicycles and the sun were on the other side of Venus, like this model shows, you'd never get a full Venus, or even a half Venus, when the sun's on the other side. Do you see how you never get a full Venus this way? Does that make sense to y'all? Venus would have to go on the other side of the sun for you to see it full, or even half. You would always have a new Venus, or just a crescent Venus. It would never get to full or gibbous Venus. And so by Galileo showing the way the phases are with Venus, with this telescope, he's able to support that the Earth is not at the center with everything orbiting around the Earth, that the sun must be at the center to be able to get all the different phases of Venus. This is a big-time evidence that Copernicus is right. And again, that goes right against what the church was telling everyone. So, bam, you're in trouble for saying all this, Galileo. And Galileo's like, look at it, it makes sense. And they're like, nope. And he's like, man. And they're like, house arrest, dude.
Can you explain waxing and waning again?
Yes. Waxing is when you're getting larger each night. Like the moon, like if you go out tonight and see the moon as a crescent, and you go out tomorrow and see this, there's a little more visible, and then the next night it's a little more visible, that's waxing. Waning is when you go out every night and it's getting you're less and less visible. Waxing and waning. Any other questions here?
Is there a solar eclipse with Venus? Or no?
Yes. Venus can move in front of the sun as we see it. Let's go back to the real model. So Venus can move in front of the sun. It's very rare. It happens twice every century. And it just happened this year. It happened in the summer, June something, and it won't happen again for 130 years. And it was a big thing for astronomers. It was in the news, even on the news. And the thing is, Venus is so far from the Earth, it doesn't completely eclipse the sun. It's just a little spot on the surface of the sun. And you can see it, though, with a telescope and a filter. And I took my telescope and filter out, and me and my dad watched Venus go in front of the sun. And it takes a long time for Venus to go all the way past it. Venus is moving, but it's so far away, it took about 6 or 7 hours. But it was cloudy the whole time, and you couldn't see it. Except for one instance. The clouds opened up, and bam, you could see it. And then they closed back up. And so we saw it. It was open for about 2 minutes. And we saw it. And I was like, yeah, I saw it. We'll have it again for 130 years. So we had a little party there, right on the beach there where we were looking at it. Isn't that cool? That was a big deal for me. And Mercury does it too. Mercury will go in front of the sun because Mercury is closer to the sun than the Earth. So Mercury will go in front of it every now and then. There's a word for it. It's called when Venus and Mercury go in front of the sun, it's called I can't think of the word. It was like an eclipse. Okay, let's talk about another guy, Tycho Brahe. You ever heard of him? He's another early astronomer. Now, he was actually before Galileo. But the book talks about it after Galileo. But Brahe was, before the telescope, he was rich. Y'all would love Tycho Brahe. He was a partier. He was a rich Dutch astronomer. He had, in modern times, if you adjust for inflation, he'd have been a billionaire. He's like Richard Branson or somebody. He's just got all this money. And he's infatuated with the stars. So he builds an observatory, which is just a tower with a chair in the middle of the room and glass on the sides so you can see out everywhere. And he makes all kinds of astute observations of the stars. He's got equipment where you can line up and tell the exact declination and right ascension. And he charts where the stars are every night for many, tens of years, for decades. He shows where this star is and where this star is and where the planets are. And he's got assistants that write down all these observations that he makes with these very simple tools that they use even today for surveying equipment, basically, is what it is. And so he makes all these observations, he writes it down and records them, and it's great data. But he was again, he didn't really have anything to do. He was born rich. And he'd have all these huge parties, and he'd invite royalty from all over, and he'd invite all these people from the town, so everybody loved him. He'd let everybody drink for free, and they'd feed everybody. And he'd have these huge blowouts, and he liked to stay up at night to look at the stars. So he was an all-nighter kind of guy, every night. And he even had this one party. He'd buy a gift for Prince. So he had a horse, real nice one that he bought. I think it was a horse that he bought for this king or this prince, and he brought it inside at one of his parties, and he was feeding it beer. And the horse was drinking beer. And the horse got so drunk that it fell down the stairs and died. And that was one of his parties. That's what his parties were like. He was such an aristocrat that he kept a dwarf under the table at his house, and he brought the dwarf out at parties and would make it sing and dance and things like that. I'm not kidding. Isn't this hilarious? Tycho Brahe, man, he was a partier. He got real drunk at a party one night. Then he decided, he got mad at this guy at the party, and he decided they would have a sword fight, a duel. And so he went out and he dueled this guy, and the guy cut his nose off with a sword. And so the rest of his life he wore a golden nose that he had made for him to replace his lost nose. And a little bit of curiosity here, he died and they buried him with his golden nose. And when they dug up his body, many hundreds of years later, to kind of see who the guy was, they found the skull and the nose was there, and it was fake gold. So that was a big, what's this billionaire doing with a fake gold nose? They thought he told everyone he had a real gold nose. So I don't know what that's all about, but he just had an interesting life. If you ever want to read just some interesting things that's real, it's not Twilight or whatever it is y'all read. Read about Tycho Brahe. Interesting stuff. He had a crazy life. So he had an assistant named Johannes Kepler, and Kepler helped take all his data. But Tycho Brahe was very stingy with his data. He would never let any one person look at all the data. He'd have this assistant keeping data, and then he'd fire him and get another assistant, and then this one, Kepler, was so good he never fired him, but he would never let Kepler look at all the data at once. But Kepler was looking at this data of where the planets were at different times, and Kepler was an amazing mathematician. So Kepler started coming up with the idea of how to predict where the planet would be the next night. And Kepler started doing mathematical equations saying, oh, I can predict the orbit of the planets. The idea going all the way back to Ptolemy and Aristotle was circles are big. And they thought the planets orbited in circles. But the circular orbits didn't give you the ability to predict just where the planets were. Kepler figured out they weren't circular orbits. Planets orbit in what's called an ellipse. Have you ever heard of that shape, an ellipse? And it went against the idea of circles. But Kepler said, I don't think it's circles. And he started doing math, and Kepler actually invented some math to figure out the orbits of the planets. And Kepler wanted all of Brahe's data to be able to figure this out, but Brahe wouldn't give it to him. And then Brahe all of a sudden dies under mysterious circumstances. And Kepler gets his hands on all the data. So the thought is that maybe Kepler poisoned Brahe. Poison was an easy way to kill somebody back at the time, because they didn't have forensic science analysis. And so if you wanted to kill your buddy, you just poison him. And that happened a lot back in the day. Now it doesn't happen. You poison someone, they'll figure it out. They can do toxicology and stuff. But back in those days, they didn't do anything like that. So they think that maybe Brahe was poisoned by Kepler, but they'll never know for sure. There's Brahe right there, and showing him and pointing to the stars. And here are some of his assistants writing things down. There's Brahe, and look, you see that piece of his nose there? That's the gold nose. It didn't knock off his whole nose, just a big chunk of it. There's Brahe, some of his assistants. There's Kepler. And Kepler's really the one famous. Have you ever heard of Kepler's laws? I'll show you Kepler's laws here. Here's Kepler's first law. The orbital paths of planets are elliptical, with the sun at one focus. We're going to draw an ellipse here. Are you ready to do a little drawing? This is an ellipse. An ellipse is almost a circle. What you do, and what we're going to do here, and I want everybody, we're going to have to go in the lab to do it. We're going to draw an ellipse. And do you see this picture in your book? Find where this picture is in your book. You go back one. Are you writing Kepler's law? Orbital paths of planets are elliptical with the sun at one focus. I want you to draw some ellipses, and we're going to experiment here. Whoops.
Wait, did you say with this?
With the sun at one focus. So what we're going to do is we're going to draw an ellipse. We're going to put down pins into a paper, and I want you to understand the point where each pin is called a focus. And the sun is always at one of the foci of the ellipse. So get up, bring your book so you can kind of copy this picture. And you'll need a pencil or a pen, and I have the paper for you. Come on in here.
Should I bring the camera?
Sure.
Might as well just turn it off.
Yeah, I don't want to do this anymore. How do I turn it off?
Yeah.
Who's videoed? How do I stop this thing?
He said bring it.
Oh, okay.
You press the middle button now.
Okay.
You can just set the camera up pointing at your table or something. And what I want everybody to do is to come up here and get a piece of cardboard. Because we're going to have to stick the pins in something. So we got cardboard up here. There should be one for everybody. Just one piece for each person. And then you need to get 2 pens, which I have here, and a sheet of paper, or you can get 2 sheets of paper if you want. Let's just do 1 sheet of paper now, and if we have extra. Get a couple pens and a sheet of paper.
Wait, a couple pins?
Yeah.
And Allie, you can point that camera at what you're doing. While you're doing it.
I don't want to point it at myself.
And then we're going to get some string.
No, it's pointed at you.
And I have string right here. Oh, let me get some scissors.
I have string.
I don't want to be in it the whole time.
I got an artist on the other side.
Mine says Tanner Hart's big penis.
Your card.
Yes, my cardboard.
Mine says you will do great.
Mine says yo mama.
You will do
Mine
great.
says Tanner. Oh, I was like, didn't your sister date Tanner Rogers? It says Tanner Hart's big penis.
I got
This is going to be on the
here.
video and he's going to hear it.
I kind of want to take a picture of that and send it to her. She'll laugh.
Hear it? Does she still date him?
No, God, no.
Tell you what I'll do. I'll cut you a piece of string.
I remember one time y'all brought me home.
And I want you to try and set up and draw an ellipse as it shows in the book. Everybody come up here and grab a piece of string and cut it. There you go. I'm just going to cut it.
You want to tie this stuff?
Cut it for each person. Look. There you go. Grab it. Each person get a piece and try and set up the ellipse. Grab. On your paper. Try and draw one. It doesn't matter how far apart your
Probably easier.
I don't have a pen.
there you go. Maybe if the next person in line can kind of grab and pull, then I won't have to do both. Yeah, there you go. Just pull down as it'll come.
Thank you.
There you go. Oh yeah, now we're doing it. Just pull it down. Yeah.
What do we do once we've drawn it?
After you draw one, what I want you to do is I want you to draw a couple more, changing how far apart the foci are. Put them real close together or real far apart and see how that changes your ellipse.
Oh, God.
Yeah. If you give them, and experiment with more or less slack of string.
There we go.
Kepler figured out this is how things orbit. Things orbit in ellipses.
It's supposed
you have a
to
good
look like
one.
an oval?
Mine's a big triangle.
Is it supposed to be an oval? or
Yeah,
is
it's like an
too
oval.
big.
Okay,
It's
good.
actually
I
called
thought
an
I
ellipse.
did it
That's
wrong.
okay. You can draw up here.
I don't have a pen.
You don't have a pen. Well, then you can't do it.
Wait.
I'm okay with it.
There you go. You're doing it.
Go like this.
Now hold this like this,
How's mine?
and then,
How's this?
oh, you don't have it. Tie it in there, and then draw. Whoops.
Okay, I'll tie this tighter.
Yeah, pretty good.
You can
There,
give
look,
yourself
I
more
made
slack,
one.
too, if you want.
I made one.
If you put this actually through,
Look at it.
how'd you make it?
Just
Put
with
your
my phone.
pencil like
Do it this side.
on the end like this, and then you just draw.
There you
like,
go.
Sorry, I can erase that, but you just, I'll do it with my eraser. Just go like that. Well, yours is, I don't know
Copy
what
the
you
picture in
did.
the book.
It's not the way mine is.
You want
Put your things wider.
I think your string has to be, actually, I don't know.
Yay, I win.
Hi.
I'm doing this one.
Stop, Ellie.
Hey, Leah.
Stop.
That was a hiccup.
Nice.
Claire's
You can
hiccup
draw on the
is
cardboard. Don't feel
Mine are
like you
super
can't draw on
long.
the cardboard. Oh, you got a good one.
I can draw.
Carson.
Yeah.
Hey.
Do this. Put the two foci right together,
Oh, mine's
where they're right side by side.
Wait, how will that work?
Oh, poop.
That's a terrible word to say. Not very ladylike.
How does that work? It's just two.
The two foci real close together. Nope, you're not doing it like that. You see how the pen actually goes through the string and holds the string down?
Oh my god. You'll slacken it?
What?
Give it a little more slack, where you get more string hanging out. So shove the string through
Oh my god, it's not working at all.
one and then the other.
Hold on, I'm gonna.
The string's just falling
How?
apart.
You got it. You can draw on the
Yeah, you are
cardboard.
clearly challenged.
Just like that?
There you go. And then wait, stop, because you're on the other side here. You got
Look
it.
at mine. I can make it a
Flip it
perfect
up.
spiral
Oh,
here.
pull it out. Get it over on the other side. There you go.
Awesome. I think I kind of messed up.
That's an ellipse.
Oh, I just made this the exact same size as it was like a minute ago.
Amateur.
Stop.
Get me on that video.
Nice.
Green horn.
Why isn't it a perfect circle?
Aha, it's not a perfect circle, is it?
No.
Well,
It's kind of an oval.
mine's a spiral. Solve a claim. I'm better than
Oh
this.
God, why?
Nonsense design. Sort of, right?
Those are good ellipsi.
Great.
Look at these. It's pretty.
Is it only second year?
Very nice. All right, let's go back.
No!
Could I use your economy book?
My economy book? Or
Econ
my...
book?
Do me a favor.
Wait, when do we have econ?
Second
Put everything
class.
back where you found it, except for the string. Just
You have
pile the
another free
string
period
up.
left, I think.
You
Because
throw the
I have
paper
Latin.
out. Pile the
people.
string up next to the string. You know, your pen.
Scott.
Put your string down next to your pen. Put your cardboard back.
video.
Awesome.
The people watching the video are going to be motion sick.
Mm-hmm.
Like Blair Witch Project.
Okay, here, what do you want me to do with this?
Except this is twice.
You keep filming. We're not.
Oh, we're not done yet?
If that's the video, that would be awesome. Well, that was your own fault, okay? You tried to do it to me. It's backfired.
Okay, so we're back at Kepler's laws. So, Kepler figures out mathematically that orbits are actually ellipses. And the sun sits at one focus. And the planet is at the line, you see, at the circle, at the ellipse.
But why is that one a circle and all of ours are ovals?
This one's not a circle, it's an oval too.
But it looks like a circle.
The more slack you give your rope, the more it looks like a circle. If you don't give your rope much slack, it'll be flatter. And the closer you put the two pins, the more like a circle it'll be.
Okay.
The planet's orbits are almost circular. That means the two foci are almost together for all the planets. And it's almost a circle, but it's not quite. It's an ellipse. And ellipses can be described mathematically, and that's what Kepler did. The sun sits at one focus. There's just an empty spot in space as the other focus. And the planet orbits in this flattened circle. The closest point to the sun we call the perihelion, and the furthest part from the sun we call the aphelion. Everything orbits in an ellipse, not a circle. That was the major contribution of Kepler. Now, he also has a couple of other laws, which are very interesting mathematically. Kepler, again, was a mathematician. An imaginary line connecting the sun to any planet sweeps out equal areas of the ellipse in equal intervals of time. And these are in your book, so you guys that are writing these, they're in your book, page 32. I got to kind of move a little bit faster here, that's why I'm saying that. Let me show you what Kepler's second law means. That's what's important for you to understand. The planets do not move at consistent speeds. Y'all pay attention here. It's page 32 in your book. It says the Kepler's laws. The planets don't move at consistent speeds. Y'all got to watch this. They move like this. They're slow over here and faster near the sun. They kind of go like this.
Why are they
Well, it moves at the same speed. It just looks like it goes faster, doesn't it? Because
it's actually going faster
Really?
near the sun. Yeah, the speed of it is actually faster. And Kepler figured out, it has to do with gravity, which we'll talk about tomorrow. And Kepler figured out that the planet, if you take...
Sorry.
Stay with me here. If you find the area that the planet sweeps out in its orbit, the area of C here is equal to the area of B, which is equal to the area of A. So, for instance, the time it takes the planet to go from here to here, well, what's going on?
I'm sorry, I keep dropping things.
What?
It's not on purpose.
Okay, well, I want to try and explain this to everybody. Okay, so the planet goes from here to here in the same amount of time as the planet goes from here to here. So it's going slower over here and faster over here. And Kepler said it's the area that the planet sweeps out. This area, all those areas are equal. Kepler figured that out. That's Kepler's second law. So again, it's going faster when it's near the sun and slower over here. And it's hard to tell because the planets' orbits are so close to circular that it's hard to tell with the planets. But his data allowed them to predict exactly where the planets would be the next day and the next month and the next year. And then Kepler's third law, which again you can read on page 33. The square of a planet's orbital period is proportional to the cube of its semi-major axis with Earth equal 1. And right now you're probably reading that and that sounds like Greek to you. But let me show you what that means. There's a table on page 33 at the bottom. So let's look at this again. The square of a planet's orbital period. The orbital period is how long it takes to go all the way around. So for instance, Earth takes 365 Earth days to go all the way around once. We'll call that one year. The Earth takes 1 year to go around once. Mercury does it in only 0.241 years. Mercury goes around the Sun about every 2 months. 2.41 years. Or 0.241 years. And so we call that the orbital period. So what Kepler's saying is the square of a planet's orbital period. If you square how long it takes to go around the Sun once, it's equal to the cube of the semi-major axis. Let's see what the semi-major axis is. The semi-major axis is the distance from the center of the ellipse to the edge of the ellipse along the longest line you can make in the ellipse. So if you take this ellipse, which is a flattened circle, and you go along its longest line, the semi-major axis is from the middle to the edge. We call that the semi-major axis. And what Kepler's saying is, if you square the period, that's exactly proportional to the cube of the semi-major axis, which is a mathematical expression. But here's the semi-major axis as Kepler measured. Well, Kepler only measured it for a few planets, but this is for all the planets now. And here's the orbital period of the planet. If you square this and cube this, you get the same number. And there it is, p squared and a cubed. It's all about the same. Wow, mathematicians said. You could probably care less about it. But these three laws help you explain exactly the motions of the planets, and no one had ever been able to do that. Even, especially using the Ptolemaic system with the Earth at the center, you couldn't explain it. But now with Kepler's laws, you can predict the position of the planets exactly. And that's what Kepler gave to astronomy.